All right, everyone, welcome to Zoom for Thought. Today we have Sam Spiro talking to us about games or something.
Yep, that's exactly it, Maki. Yeah, so all this is going to be joint work with these lovely people, Percy Diaconis, Ron Graham, and Xiaoyu He. I'll also note that I'm giving this same talk again in 2 days. So if at any point I'm saying something that's like boring or you don't understand or there's a typo, one, just interrupt me during the talk. But if not that, tell me about it within the next 48 hours, if you can. Okay. And as Maki mentioned, today we're going to be playing some games. And to start off, I want to volunteer from the audience to play some games. So Maki, would you be interested in playing a game? It's combinatorial in nature, if that helps sway your opinion.
That does help. No, thank you.
Okay. Greg, would you be interested in playing a game?
Yeah, sure. I'll play a game with you, Sam.
All right, perfect. All right, so what we're going to do, Greg, is I have this deck of playing cards shuffled roughly uniformly at random. And I want to test if you're a psychic, right? And the way we'll be doing this is I'm going to pick up the top card. Ignore that you saw the bottom card. And I want you to guess what this card is. And it's too much to ask that you get the suit right. So just tell me if it's like a 2 or a 7 or a king. Just what are you getting? What kind of image are you thinking?
4.
4? I'm sorry, it was actually an 8. Okay, but we'll continue.
Oh, I should have done both hands.
Yeah, that was the one thing.
My bad.
Yeah, it's that whole left-hand rule. It was actually the left-right-hand rule. Okay, so now I picked up the next card. And given that the card I just discarded from the deck is an 8, what's the one card you shouldn't guess, assuming you're not psychic and have no idea what this is?
8.
Exactly. Should not guess an 8 because there's only 3 copies left in the deck, and there's 4 copies of everything else. So do you have a guess for this, Greg?
Yeah, Jack.
Jack, it was actually an 8, ironically. But you did do the correct choice.
Wow. I feel like this game is rigged.
I assure you, Greg, at this point, the game is not rigged. So more generally, the game we're going to be considering has a deck of size MN. And the deck is composed of N different card types, and each card type appears with multiplicity M. All right, so just to make sure we're all on the same page, when N equals 13 and M equals 4, this corresponds to a usual deck of playing cards. We have 4 suits, i.e. each card type appears with multiplicity 4, and there are 13 card types, 1 through 10, Jack, Queen, King. All right. So to begin the game, the deck is shuffled uniformly at random. And each round, the player, who I named Guesser, or Gregor, tries to guess what the next card in the deck is. And after each guess is made, I reveal what the card is and then throw it off to the side. And each time you guess it correctly, you get a point. And this continues until the deck is depleted. And this game is called the complete feedback model because after each guess, you're given complete feedback of what the card actually was. And I'll note that this game, in addition to being just a fun thing to play with your friends over the weekend, also has some real life applications. So it was apparently introduced to study certain aspects of clinical trials, and it was actually used for ESP detection experiments. Okay, so that's the game, and now I want to analyze it. In particular, I want to figure out how well certain strategies do in this game. So we'll let bold G be a strategy for the guesser, some way of figuring out what the next card to do. Yes, what is ESP detection? Yes, so ESP stands for extrasensory perception. So it's basically psychics. To see if someone claims they're a psychic, they can read minds, they can see through walls or whatever psychics can do. So yes, I should have clarified that. Thank you. Okay, cool. So we're interested in the strategy G and how well it performs, and we'll define C of G to be the expected number of points the guesser gets if they follow this strategy G and if the deck is shuffled uniformly at random.
How many guesses does the guesser get?
MN. So they just run through the entire deck.
Oh, okay. Until
it's depleted. So hopefully they should get the last one correct if they're paying attention and if they want to maximize this. So as an extremal combinatorialist, I'm interested in the extremal values of this function. Namely, we'll define C plus to be the maximum number of points you can get through any strategy. We'll also consider C minus the minimum score you can get with any strategy.
Also, how do you formally define a strategy?
Yeah, so basically it's, so to do it so we'll just consider discrete strategies. We'll say, given that you know the discard pile was this, choose the next card type. So it's a function that takes in and you can really do it. It makes a random variable with your card choice, but there's no reason to. The optimal strategies you can prove will be deterministic, can be chosen to be deterministic.
Cool, thanks.
Yep, thank you for that. Yeah, and again, do feel free to ask at any point. But yeah, so C+ is the maximum we can expect to guess with any strategy, and C- is the minimum score we can expect to get with any strategy. And so intuitively, like what Greg worked out, is that if you want to say maximize the number of points you get, what you should do is each round, you know what the discard pile is. And given this, you can compute the probability that this next card is a 2 or a 7 or a king. And once you compute all these probabilities, you should just guess what the most likely card is. That if you want to maximize your score, that's what you intuitively should do. And it's relatively easy to prove that this is indeed what you should do. And moreover, so this was proven by Percy and Ron back in 1981. And they moreover proved what this maximum minimum quantity is when n is fixed. When you fix the number of card types, but you let the multiplicity of the cards grow arbitrarily large. And it turns out to be roughly m plus or minus, depending on if you want to maximize or minimize the score, square root of m plus some lower order terms. And moreover, they got a very tight bound on what exactly this concept is. So that's nice that we know very much about this, but I have to say something interesting in this talk, so I'll have to do something else here. So we're going to have to consider a different game. So Greg, would you be willing to volunteer again?
Yeah, I'm ready to go 0 for 2 or 0
Right.
for 3. Yeah.
So the way this game's going to work is very similar. Again, I want you to guess what this card is, but there will be a bit of a twist. So why don't you guess it, and we'll see how this goes.
Like just the number?
Yeah, just the card type again. Yes.
Yeah,
Exactly.
3.
Okay. Now, what do you think this next card is?
That's a different card.
That's a different card.
Okay, a 5.
Okay. So if you notice, I didn't tell you anything about that first card that you guessed. So you might have been correct. You might have been wrong. Spoiler alert, you were wrong with both of them. But this is what's known as the no feedback model. Now, as opposed to telling you exactly what the card type was, I tell you absolutely nothing about the card type. And because it's too hard to argue that whatever strategy you cook up, you'll always get exactly m points guessed correctly in expectation, because every guess has exactly probability 1 over n of being correct. All right. So again, this isn't super interesting because it's very easy to solve. So we'll make one last adjustment. So Greg, if you're willing, one more time. So again, same sort of rules. What do you think this is?
Queen.
No. Okay, so I told you a little bit more. I told you that you're wrong, which is always fun. But now, given that this card is not a queen, you said queen, right?
Mm-hmm.
What's the most likely card that this is?
Wait, did you shuffle the deck again before doing this example?
Yes.
Okay, right. So it's most likely to be a queen.
Exactly, because there are exactly 4 copies of a queen left in the deck, and every other card type has a slightly smaller expectation for what it is. If you were to guess this was a queen, you would also be wrong. But now you're increasing the probability that it is a queen, and certainly eventually you'll get that it is indeed a queen. So this is what's known as the partial feedback model, where I give you a bit more information. Namely, I tell you whether your guess is correct or not, but not the true identity of the card. And we have a comment in chat. Yes, that is correct. Greg, you should maybe not press your luck with gambling. All right, so yes, so this is the game we want to consider. We have achieved our goal of this being an interesting model. Oh man, the chat is great. It's a shame if you're not here for the live event, you're missing out, really. So the partial feedback model is genuinely interesting in that we don't immediately know how to solve the problem, and particularly we don't know what the optimal strategy in this game is. So for the complete feedback model, we knew just guess the most likely card. For the no feedback model, we knew just do whatever. But for this, it's not totally clear. And furthermore, we know a strategy which isn't optimal, and that is, so it turns out that guessing a most likely card each round, while more difficult to analyze, also isn't an optimal strategy. There are weird situations where even though you know this next card type is most likely to be an ace, for some reason you should guess a 2 instead to maximize your score. And the vague heuristic I have for this is that somehow guessing a 2 in this instance gives you more information. Somehow getting a no answer there tells you more. If that heuristic doesn't convince you, that's fine. It doesn't entirely convince me either, but it's a fact that I know is true. So let's just all accept that this is the case for whatever reason. Okay, so we don't know what the optimal strategy is, but we can still attempt to try and understand what the optimal score is, or at least bound it. So as before, we'll let P of G denote your score in the partial feedback model when you do this strategy G, and we'll let P plus and P minus be the max and min scores that you get respective strategy.
Wait, Sam, I
Yes.
have a small question,
Mhm.
and perhaps you're going to go into this, but for this partial feedback model, does an optimal strategy or a better strategy or something involve some kind of exploration period, or is it kind of like you keep varying it throughout somewhat to make sure you're getting new information?
Yeah. So basically the short answer is I don't know, or no one
Okay.
knows, because we don't know what the optimal strategy is.
Right.
It's conjectured that the optimal strategy satisfies something called the persistence conjecture. So it says that if you guess this is a 2 and I say you're wrong, then you should also guess that this is a 2. Basically, if you guess something and you're wrong, well, now you just know even more so that it's likely the next card to be that. So you should just keep guessing. This is a conjecture. It's not known to be true, but that's the only kind of structure that we think is true for the optimal strategy. Does that make sense?
It's like the gambler's fallacy, but it works.
Yeah.
Yeah.
Exactly.
Thanks.
Yep. Okay, yeah, so we have this max and min score, and we want to try and determine what it is. And we can do this with some kind of dumb bounds. So first of all, the max score you can get in expectation is at least m. Namely, you can consider the dumb strategy of just guessing 1 the entire time throughout the game. That will certainly get you m correct guesses at the end of the game because there's m copies of card type 1. It's also the case that this quantity is at most the maximum score you can get in the complete feedback model, because you can certainly just ignore the extra information you get in the complete feedback model to reduce to the partial feedback model. And by this result of Percy and Ron, we know that this quantity is roughly m when n is fixed. So we've solved the problem. We know that P plus is asymptotic to m, and the same kind of analysis shows that also P minus is asymptotic to m whenever n is fixed. So while this is correct, it's again not particularly interesting. So that's unfortunate. But if you'll notice, every time I've said something here, I've always had this assumption that n is fixed, the number of card types. So it's natural to kind of ask, what happens now when the number of card types grows to infinity and we let the number of suits in our deck stay fixed? And this turns out to be interesting, or at least in my opinion, it turns out to be interesting. Certainly non-trivial. So our first result in this direction is tight bounds for the complete feedback model when the multiplicity of your cards is fixed and n is tending towards infinity. In particular, the maximum number of points you can get is the nth harmonic number times log n, and the minimum score is n to the minus 1 over n. And I won't go too much into the details here, but I'll note that this result, while non-trivial, is relatively straightforward. Namely, we know what the optimal strategy is in the complete feedback model. It's just this guess the most or least likely card each round. So this result doesn't need any game theory. So, Vaki is very happy. It's just computing the expectation of some weird random variable. That's all this really boils down to at the end of the day. And again, I won't go into the details, but I'll just give you a bit of a flavor for how this proof works. So for example, a lemma that we need is that with high probability, after n to the 1 minus 1 over m rounds, some card type gets depleted from the deck. In other words, maybe we run out of sevens after about this many rounds. And you can do the computation, and it shows that before this event happens, while you still have every card still has a copy in the deck, the probability that any guess is correct is roughly 1 over n, the number of card types in the deck. So in expectation, the total score you get in this period is these two things times each other, which is exactly this quantity here. And after this event happens, if you want to minimize your score, then you can just guess this card type that's no longer in the deck, and certainly you'll get it wrong every single time. So that gives you in total this many cards correctly at the end of the game. So that proves this C minus bound, and the C plus bound is also a similar kind of proof. Okay, so that's what we have. And with this, we can go back to our trivial bounds on P plus is again at least M, and again at most C plus M n, which we now know is roughly of the order log n. And so this is non-trivial, well, I guess they are trivial bounds, and there's still quite a big gap between these. If we're thinking of M as some fixed constant, this is constant, and well, this is tending off towards infinity as n tends towards infinity. And a priori, it's not clear which of these two behaviors P plus actually satisfies. So again, here are the trivial bounds. And our main result is improvements to both of these bounds. So first of all, we improved the lower bound by a smidge. Namely, we have a better strategy in the partial feedback model than just guessing 1 every single time. We can be a bit smarter and gain this many points in expectation. But most importantly, we have a tight asymptotic upper bound. So we improve that in P plus, no matter what strategy you cook up, you won't get more than M points correct in expectation, plus some little error. And kind of the heuristic for what this is saying is that with partial feedback and M fixed and N tending towards infinity, you can't get many points correct compared to having no feedback at all. So recall in the no feedback model, we got M points every single time. And this is saying maybe you can do a little better, but not really when N is growing to infinity. And this is somewhat intuitive because in the partial feedback model, assuming you're incorrect, if Greg's playing, then the feedback I give you is that this card type is not of type I. And if we only have 2 types of cards in the deck, that's very useful information. That completely determines what that card is. So if I have only deck types of 1 and 2, and I tell you that card type is not 2, then you know for sure that card type is 1. But now, if I tell you there's a billion card types in the deck, then me just telling you it's not 2 really doesn't tell you much about the situation. So that's kind of the intuition for why this should be closer to M, but certainly it's far from it. So does anyone have any questions right now about the current setup of things? Okay. So for the bulk of the talk, I'm going to be talking now about a rough proof of this, though it certainly won't be complete. The key lemma we need is going to be this thing, which will take a bit of time to develop. So say we've played this partial feedback model for T-1 rounds, and we're now thinking about possibly guessing card type I. And we're given 2 pieces of information. The first is that we've already guessed card type I a total of GI times. And the second is that we've already scored S points total. So we've gotten S cards guessed correctly. So the lemma is that, let me go back to this theorem statement. Yes, so this big O.
So, Sam,
yeah.
Just for the recording, I'll read the question.
Great idea.
Sorry, but in the upper bound, M is constant. So what is big O referring to here? Or did I misunderstand?
Yeah, so you, yes, you do not misunderstand. So this is, yes, what is the exact statement here? Yeah, so this is slightly incorrect. What it should be saying is that for any M and N sufficiently large in terms of M, you have this upper bound here. So we are thinking of M as growing, I guess, slowly to infinity, and with N growing much faster. So this bound is only effective. So really, you could think of this bound as being, say, M plus 10 billion times this quantity here. So it's only really effective when M is of the order of 10 billion at least. And it only applies when N is at least 2 to the 2 to the M or something to that effect. Does that help answer the question, Thomas? So I guess it's the opposite. So basically, yes. How do you state this rigorously? I should have just copied whatever we wrote in the theorem statement. Okay, so I got sure. All right, was sure referring to, let me just state it again in case you weren't so clear. So we have M. So yeah, again, I'll just stick with my result of it's M plus 10 billion times this quantity here, provided N is sufficiently large in terms of. That will be my statement. Hopefully that clarifies. If not, please ask me. But yes, so let's accept that the theorem statement makes sense. And I'll take note to do that again, to edit that before the next talk. Okay, so the claim is if we're told I has been guessed GI times, and that there are a total of S cards have been scored, then the probability that the next card type is I is at most this quantity here. And I won't bother to prove it. It's some relatively straightforward combinatorial argument, but I just want to give some intuition for what it's saying and why it might be true. So in particular, this upper bound is most effective when GI and S are both small. If GI is close to MN, then this says that this probability is the most like roughly infinity, which is not particularly useful. So this bound really only applies when GI and S is small. And the intuition for why this is true is that these sorts of conditions are necessary for any reasonable upper bound to hold. So for example, if we happen to be in the case where we've guessed card type I incorrectly a total of mn minus m times, then we know the next card must be card type I, because there's m of them left in the deck, and we know they weren't the first mn minus m. If you plug in GI here into this expression, you get that it's at most 1, which is as best as you could hope to do. And similarly, if you scored mn minus m cards correctly, and none of them were equal to I, then again, you know the next card type must be I. So similarly, the best upper bound you can prove is at most 1 in this case, which agrees with this limit here. So again, I'm not proving anything here, but this is kind of the intuition for why you need GI and S to be small in order to apply this bound for any. So this, again, I should emphasize, holds no matter what's happened in the game up to this point. If you just tell me these two pieces of information, it holds no matter what's happening. And for this to be true, we need some kind of condition like this. Okay. So that's going to be our main lemma. And again, to apply this lemma, we need to make sure that S is relatively small. And we do this with the following other lemma, which says that no matter what strategy you use, with high probability, your score S won't be very large. And this is a bit of a chicken and egg problem, because the entire goal of this proof is to show that S is relatively small. And here this lemma is saying that, oh, it is small. But the reason this is fine and like not that hard to prove is that the bound we're proving is like epsilon times mn. And if epsilon is like 0.001, this is very, very large compared to the real bound of m that we're trying to prove. So basically, this says that if we were just trying to prove a very weak bound on our score, we can do it relatively easy and say this happens with high probability. Okay. So these are the two main lemmas we need for this proof. And with these alone, we can give a relatively short proof of a pretty tight asymptotic upper bound of roughly 3n. So let me just demonstrate how to do that, if only to give us some practice with how these lemmas work in practice. Okay, so what we're going to do is pretend our score S is 0. Basically, that second lemma said we can assume it's epsilon mn with high probability. So this is basically true up to epsilons and whatnot. Then applying our first lemma, we have the probability that at any point that our next card type is I is at most this quantity here, where GI is the number of times we've guessed card type I. And as I mentioned, in order to apply this bound effectively, we need GI to be pretty small. But this won't always be the case. Someone could just guess card type 1 throughout the entire game. And certainly by the end here, this bound will become ineffective. But the good news is they can only do this for one card type. Somewhat more precisely, there's at most one card type I, which is guessed more than half the time for kind of trivial reasons. And this card type can't be guessed correctly more than m times because there's only m copies of it left in the deck. So we'll just assume worst case scenario that whatever card type the opponent guesses the most gets correctly m times. All right. So now given that, and once we throw out all those guesses, every other card type has at most mn over 2 guesses each time it's guessed. So plugging that into this formula here, we get the probability that any of our other guesses is correct is at most 2 over n. And now just kind of a linearity of expectation, there are mn total guesses we'll make. And each of them has probability at most 2 over n as being correct, assuming they're not guessing this most likely card. So that gives us 2m correct guesses from this part of the problem. And if we add back in the m guesses the m cards we threw out, that gives 3m guesses correct. So that proves this thing. And I'll note that there is certainly some slack in this argument that I just gave. In particular, it's not too hard to improve this to roughly 2.7 M. But I'll warn you that if you want to go home and try and boost this number down even further, you have to be very careful with how you condition these random variables. So for example, while I was prepping this talk, twice I thought I could use the same method to bring this 3 down to a 1.7, but this turns out to be too good to be true. So then I had a minor panic attack of the whole paper being wrong and me having to give this talk in a couple days. Fortunately, I found errors and everything is fine. But again, it's very easy to miscondition your random variables in the setting. So you have to be very careful. And we'll see a couple examples of that later on. So any questions about the sketch or the main lemmas we have or anything else? Okay. Right. So now we have this pretty good upper bound, but we want to get it as tight as possible. So to do this, the idea is no matter what the strategy D is that our opponent is using, we want to somehow say that the number of correct guesses they have is concentrated in some sense. So an example of concentration that we would like to have happen, but which turns out to be far too good to be true, is that if card type I has been guessed roughly alpha mn times, then we want to say that with high probability, it's been guessed roughly alpha m times, or certainly at most. So if this were true, then we could say with high probability, the number of correct guesses at the end of the game is at most the sum of this quantity, which is just m, which is exactly what we want. But unfortunately, this can fail, in particular when card types are guessed very few times. So for example, what the guesser could do is they could guess 1, then 2, then 3, ... up to n. And it's very likely that within these first n guesses, one card type is guessed correctly. Again, let's say it was 7 was guessed correctly. So now they've guessed 7 a total of 1 time, and they were correct 100% of the time, basically. But we want to say they were correct closer to 1 over n. So there's a very big gap between what should be happening in expectation and what actually happens for this guess. So this kind of concentration we just can't hope to. But to get around this, what we can do is consider all n of these guesses simultaneously. And more precisely, we'll say that a guess involving a card type I is subcritical if this I has been guessed at most epsilon mn times, where epsilon is some small constant. So in other words, or for example, up here, because each card type was only guessed once, each of them would be considered a subcritical guess. So now, instead of concerning ourselves with saying 1 was guessed the correct number of times, 2 was guessed the correct number of times, and so on, we now just say all these guesses, which guess cards that have been guessed few number of times, were correct roughly the right number of times. So because we can now lump all these things together, it is actually possible for us to get some concentration, as I'll illuminate over here. So to be more precise, we'll let T naught be the total number of subcritical guesses that we've made during the game, and we'll let S naught be our score from these subcritical guesses. Now, by our lemmas, we know the probability that any given subcritical guess is correct is at most this quantity here, because that's always the case. But because we're subcritical, we know that the number of guesses at this point is at most epsilon mn. That's what the definition of subcritical is. And again, if we just ignore the fact that, if we just pretend that S is roughly 0, this quantity here is roughly 1 over n for each of our subcritical guesses. And with this, we can basically approximate S naught by a binomial random variable, which has T naught trials with probability of success 1 over n. So this is nice because binomial random variables are highly concentrated. We know that a binomial random variable with T naught trials has concentration around T naught. The problem is that this holds when T naught is a fixed integer, but that's not the case here. T naught is a random variable, and in particular, a random variable depending on whatever strategy our opponent wants to choose. And because of that, we can't just naively apply concentration results. So kind of to illuminate what an issue that could happen is that what the guesser could do is they could just keep making subcritical guesses until concentration fails. So if you look at any given timestamp while the guesser is making subcritical guesses, it's pretty likely that the quantity is going to be close to this mean here. But if they're just allowed to just keep making subcritical guess after subcritical guess, it seems plausible that eventually at some timestamp, the number of correct guesses will actually be something like twice this mean. And then they can just stop making subcritical guesses and go off and do something else. So because of this possibility, we can't just naively apply the Chernoff bound to get our concentration. And what we actually end up needing is a sort of adversarial version of the Chernoff bound. So we'll let B be a random binomial random variable with 1 over n trials and mn, or 1 over n probability and mn total trials. And we'll also look at BT, the number of successes we have after the first T trial. And the result we want to prove is basically the probability that there's some T where after T steps, our number of successes is significantly larger than the expectation is exponentially small. So again, if we just wanted to have this result hold for a given T, this would be automatic from the Chernoff bound. But because we want this to hold for all T in this range, it does not follow immediately from the Chernoff bound, and you have to do some more work here. Does anyone have any questions about the statement here or why we need to do this? Okay, so I'll briefly talk about the proof here and mainly how not to prove the result. So as I mentioned before, if you just wanted to prove this result for any fixed T, you just apply the Chernoff bound and you get that this holds with probably roughly this quantity here. And naively, what you might try and do then is to just use a union bound for each T, just sum up these probabilities. And you can do this, but the problem is that the upper bound you end up getting is roughly n times e to this quantity here. And we're thinking of m as large but fixed, and n tending towards infinity. And because of this, very quickly, this bound just becomes irrelevant in the regime that we care. So this naive union bound doesn't work, but I claim that if you're a little more clever with how you do your union bound, you can indeed get this quantity to work out as I stated, but I'll ignore the technical. And lastly, I just want to make some brief comments about the optimality of this result. So as I mentioned, the best possible upper bound you could prove of this form is roughly e to the minus lambda squared m, again, just from one application, the Chernoff bound. And it's not clear whether this or this bound that we actually prove here is close, where we have a lambda cubed, is closer to the truth. And I'll note that if you can bring this lambda cube down, that will improve our error bounds of our theorem. So that's personally why I'm interested to know whether this is tight or not, but also I just think it's kind of a natural question to ask or independent of interest how this adversarial binomial Chernoff type bound works. And again, if you can improve this, I think it might be not too hard because again, all we did here was a union bound at the end of the day, no fancy probability tools. So if anyone in the probability community listening wants to go and solve this, maybe it'll be easy, and I would be at least interested in that. But that's all I'll say here. So again, here's our technical lemma. And with this and our intuition that S0 is roughly a binomial random variable with some unknown number of trials, we can get the concentration result that we were looking for. We can prove that with high probability, the probability that S0 is much larger than its expectation, whatever that expectation ends up being, is quite small in terms of that. Okay. So now we have most of the tools we need to prove the result. So in particular, what we've established is for the subcritical guesses, we know basically how many correct guesses are made. We have good concentration by that lemma I just stated. So those are easy to deal with. And recall that subcritical guesses meant the card type was guessed at most epsilon mn. But there's still other kinds of guesses that could be made. For example, we'll define critical guesses to be those that guess a card type between epsilon mn and 1 minus epsilon mn. And basically, if you do kind of the same argument I sketched before, you can also get concentration results here. The only slight change is that you now need to use hypergeometric random variables instead of binomial random variables, and you have to be, and there's some other fun technical details, but I'll ignore them for the moment. And if this is all that happens, then we get the result. So if these two types of moves, which we have concentration for, are the only types of moves that happen in the game, then we can say with high probability we get the result. So the only issue now is that if some card is guessed more than 1 minus epsilon mn times, which is the only case that we haven't dealt with. But in this case, we can kind of proceed as in the 3m proof that I mentioned before, because there's only one card when epsilon is sufficiently small, which can be guessed this many times. And we'll just assume worst case that we get m correct guesses from that. And now the remaining guesses are all going to be subcritical, and there will be few of them. So we can say that with high probability, there aren't too many of them. And if you put all these numbers together, you end up getting the result that I claimed. So any questions at this point about anything? Okay, cool. So next I want to talk about some of the open problems we still have left here. So again, here's the main theorem we have. And while it is asymptotically tight, it would be nice to know which of these error terms are closer to the truth. And currently, we think that the lower bound is closer to the truth. In other words, the maximum number of points you should be able to get is m plus m to the 1/2, maybe plus some, say, logarithmic terms or something like that. And I'll note that if you wanted to try and prove this, in particular improve these upper bounds here, the most obvious way to attack it would be to improve this bounds of this adversarial turnoff bound that I mentioned. And if you could prove it to its theoretical limits, you would boost this 3/4 down to a 2/3. But to improve things from 2/3 to a 1/2, you would need some new ideas. And we briefly talk about these in the paper, but I won't get into the details with that. Okay. So this was all about P plus, the maximum number of points you can get in the partial feedback model. But we can also ask what happens in P minus when you want to minimize the number.
Can I ask a quick question?
Yes, you can.
Have you done any computer experiments for your adversarial turnoff?
I have not. No, that would be a reasonable thing to do, but I have not done that.
I don't know computers, but I thought that would be probably helpful.
Yeah, no, that would be a very reasonable thing to do. Yeah. We also have a message in the chat. Yes, agreement. Cool. Yeah, so it's a very reasonable thing to ask that. I should do that. That is a good idea. But in any case, right. So now we want to talk about the minimum expected score you can get in the partial feedback model. And again, we have kind of trivial bounds. We know it's going to be at most m from the strategy just guessing 1 every time, and it'll be at least the minimum score you get in the complete feedback model, which we know is n to the minus 1 over m. So again, we have this dichotomy. The one bound is basically constant, while the other is tending towards 0. Again, a priori, it's not clear which of these is closer to the truth. And in some sense, again, this m bound is closer to the truth. So we can prove for P minus that you have this asymptotic lower bound, which is in particular a constant. You can prove that the minimum score is not tending towards 0. So that's non-trivial. And the proof of this is kind of stupid. So all this bound is it's the probability that you guess at least one card correctly in the partial feedback model. So certainly the expected score you get is at least the probability that you get one card correctly. So that's all this quantity is, and we can prove that this and that at least this quantity here. But we believe that in actuality, it should once again be asymptotic to m for various heuristic reasons. So because we have this P plus formula, we know that you can't use partial feedback to get many more points than with no feedback. And surely then you can't use it to get much fewer points with partial feedback. It seems very strange to me that this would be true. But at the moment, we don't know how to prove this. And in particular, new ideas would be needed even to prove that this quantity is at least 1 asymptotically for m sufficiently large. Okay. So as I kind of mentioned in the beginning, is that our asymptotic theorem only really gives effective bounds on P plus when m is large. And it's kind of natural to ask what happens when m is small.
So Sam, we got a
Yes.
question in the chat. Max, do you want to ask it with your microphone? You don't have to, but you can.
Sure, yeah. I was just wondering, because you mentioned heuristically, kind of you would expect the relation that you see on P plus to hold for P minus. I was wondering, are there kind of types of reduction arguments between P plus and P minus, or like C plus and C minus, or on related problems?
So could you say more about what you mean by reduction argument?
Like if you could prove that you can only get m plus something for P plus, you could prove that you could only get m minus something for P minus or an easier, a looser bound than that somehow?
Sure. Yeah, that's a reasonable question to ask. Offhand, I don't think so. So for example, for the complete feedback model, right? We know C plus is roughly log n, while C minus is this quantity tending towards 0. So there certainly you can't get this like m plus minus type bound in the complete feedback model, at least when n is fixed. When m is when n is growing to infinity. When n is fixed, Percy Ron's result does say that you do have this plus minus result. But because it doesn't hold when n is tending towards infinity, I would kind of doubt that you can do this reduction argument. But I don't know offhand. That's a very reasonable question to ask. But offhand, I don't know / necessarily think so. Yeah, good question. Okay, yeah. So now I want to talk about what happens with small m, which is again some case that we haven't really included. And so Percy and Ron got asymptotic formulas when you have one copy of each card in the deck, and they proved it was asymptotic to E minus 1 if you want to maximize the score, and 1 minus 1 over E if you want to minimize the score. But critically, their proof used that we know what the optimal strategy is when m equals 1. It is just the guess the most likely card strategy. But it seems difficult to do this for fixed small m because we do not know what the exact optimal strategy is. And we can improve our bounds somewhat. So for example, that 3m bound I showed works for small m, so we do have some upper bounds. We can also cook up some specific strategies which do give effective lower bounds, which I included a bunch of things in case I talk too fast, but we'll ignore this for the moment.
Sam, can I ask a question really quick?
Yes, you can.
So what if you take, so m is the number of different cards, right?
M is the, no, n is the number of different cards. M is the multiplicity of each card.
M is the multiplicity. Okay, sorry, never mind.
All right, cool. Yeah, no worries. Okay, so I have to be careful here. Okay.
Actually, well, I do have a
Yeah.
question related to that then, I guess.
Yes.
So in the n growing regime, so if you have n large, then you can kind of reduce it to n over 2 by saying like you take the strategy and you just have this like 2-to-1 map. Like anytime I guessed either of these two cards in the full space, then I choose this card in the n over 2 game.
Sure. So you're saying
Does
like,
that make-
yeah. So you consider you play the game twice, basically, is what you're morally saying, right? With both sides n over 2. Is that what you're saying?
No, I'm just playing it once of size n over 2, but my strategy is that like I consider two colorations of the card, and if I would have guessed either of those options, then I merge them and guess that card in the n over 2 game.
I see.
Does that take a optimal strategy to an optimal strategy?
Maybe in the complete, I would doubt it for the partial feedback model, but I don't know. I don't know offhand. That's a reasonable. I'll have to think about that a bit offline. I don't know, but that's a reasonable thought. Yeah, thanks, Tom. Okay. So the last thing I want to talk about in the couple of minutes I have is one more game. So Faki, this is your last chance if you wanna get in on the game action. If you want.
You know what? I think I will not. You may pick someone else.
Okay. Greg, are you up for one more?
Ooh, let's go.
All right. So the rules are going to be again very similar to the complete feedback model, but the rules will change just a little bit when two card types are revealed. So you'll see what happens when that happens. All right. So what do you think this is, Greg?
5.
All right. It was actually an ace.
Okay.
All right. But now we'll continue. And what do you think this is?
A 5.
Nope, it was an ace. So it was the least likely card, but yeah, it happened twice. What are the odds? All right, so what do you think this is?
5.
It was actually a third ace.
Oh my God,
okay.
dude, you're screwing with it.
All right, finally. All right, now, Greg, what do you think this fourth card is?
A 6.
It was actually an ace.
Okay.
So that was rather remarkable. So if you look at if you do the computation, the probability of getting 4 aces in a row with the deck shuffled uniformly at random is roughly 1 in 270,000. So because of this, one of two things must have happened. Either you were really unlucky, Greg, which based on past performance is plausible. But maybe you're more likely thinking that the deck was not shuffled uniformly at random. And indeed, I just had the 4 aces sitting on the side of my desk at the beginning of the talk, and I just placed them on the top of the deck for this game. And of course, if I was doing this talk in real life, or in person rather, I wouldn't be able to get away with this trick. So the main change was that this wasn't just a simple card guessing game. This was an online card guessing game. So more generally, what's going on here is that we have a 2-player game now. So now I get to do something. And the way the game works is first, shuffler takes the deck and shuffles it however they would like according to their favorite distribution on permutations. And then guesser plays the complete feedback model on this pre-shuffled deck. And I'll note that mathematically, it's equivalent to consider the game where instead of pre-shuffling the deck, just every round I look at the remaining cards and just pick my favorite one and use that as the next card, and then iteratively do that. In theory, that shouldn't matter, at least for the mathematical analysis for optimal strategies. But I'll warn you, if you try and do this with your friends, they might object to you just doing this and picking the next card. Much better to do the other. But in any case, we'll define CGS to be the expected number of points that guesser scores if these 2 players follow their respective strategies. So for example, if shuffler follows a uniform strategy of just shuffling the deck uniformly at random, we recover exactly the bounds we had before for any strategy. And the question you might ask is can shuffler do better? So if they want to have guesser score fewer points, can they decrease this HM log n term to something smaller? And it turns out they can. Namely, they can drop it all the way down to log n, and this turns out to be 10. So basically, when n is growing, the m term doesn't matter at all for the score, which is perhaps somewhat surprising. So even though we keep increasing the number of copies of each card in the deck, in theory giving guesser more chances to score, somehow he can't actually use that when shuffler uses the right strategy. And I'll note that this theorem is really a first for me. So typically the way I do math is, I solve a problem, write a paper, give a talk, tell some jokes. But here I did the reverse order. I came up with this joke of putting the 4 aces on the top of the deck, and then had to come up with a theorem to justify actually talking about it at a seminar. So that's what this is. And I'll very briefly sketch what the argument is. And it's a sort of greedy strategy where if we have, say, 10 different card types left in the deck, we'll pick each card type with probably exactly 1/10, regardless of what the multiplicity is of each card in the deck. So for example, if our deck has 100 copies of 1 and 1 copy of 2, we'll draw both 1 and 2 with probability 1/2, even though there are much more copies of 1. And it turns out, because of some known results related to coupon collector problems, this gives the log n bound. And you can also prove guesser has a strategy where he can guarantee the score. And we're a little low on time, so I won't delve into the philosophy here, but I conjecture that this greedy strategy is indeed optimal, though there are some roadblocks. In fact, I thought I had one proved this, but I made the mistake of not cleaning up my notes and then ignoring them for several months. And when I went back to look at them, I had no idea what I was trying to do. I kind of knew what I was trying to do, but ultimately I don't know what was going on. So I think this is true, but I do not actually know how to do it. And lastly, so we've talked a lot about card guessing with various kinds of feedback. So now I want to talk about talks with partial feedback. And this is also much harder than giving them with complete feedback. So I can fortunately see a couple of your faces, so I can see reactions of when my jokes are or are not funny, or more importantly, when my math is good or not good. But it's certainly a lot harder. And I'm always happy to hear from more feedback, especially within the next 40 hours, where again, I'm giving this talk again. So if you have anything you would like to say about this, please do feel free to email me, or if you'd rather remain anonymous, you can use this link here, which is also on my website. And with that, I will end the talk.
All right, let's unmute or chat and thank the speaker. All right, does anyone have any questions? And feel free to use your microphones.
I have a suggestion.
Yes.
After this experience, you need to change the last section to online card gaslighting.
That is a suggestion, and I thank you for giving it.
Like,
Greg, were
So
you-
this is yeah, sorry about that. This is I'm not sure if this is well formulated or not, but on some level, right? So the name is partial information, and a priori, you know, just hearing this, it's not clear which partial information necessarily you would give, but there's kind of a big divergence between, like in some case in this upper bound or whatever, between the full information and the partial information. Is there sort of a gradient there? And have you thought about this? You know, let's give 2 bits of information. Let's give 3. Let's, you know, I don't know.
Yeah. No, that is a very reasonable question. We have briefly thought about this. So I know
Okay,
like
yeah.
one other thing we considered was like this strategy of this information where you guess it and I say, oh, you were close. You were off by 1, let's say. So that's another thing that was considered.
Right.
Ultimately, we didn't prove anything except for this
Yeah.
here, but
Yeah.
that is definitely a good question of like, what is the threshold where you start to have, say, like log n score? What kind of
Right.
information?
Yeah.
So
Okay,
that's-
cool. Yeah.
Yeah, that's a very good question. Yeah.
No.
That one's definitely deserving of the recording. How many variants can you play until you run out of friends? Very good. Thank you.
In my experience, half. You play half a game before you run out.
Okay.
Sam, I think it's been like, you know how the government declassifies documents after a certain amount of time?
Mhm.
It's been 4 minutes after the talk. So can you declassify whether you were screwing with Greg at the start of the talk?
Oh no, that was complete. That was complete luck of the draw.
Oh, okay.
And if you notice, I said at this point in the time, the game is not rigged. So I
Hmm.
did. I was
Brings
trying
joy to
force-
my heart.
Yeah.
Well, Chekhov's Sam Spiro.
All right. Anyone else have any questions?
Wait, can I ask another one?
Yes.
Yeah, please.
There's there's a limit of 10, but you're fine at now.
Oh, come on. Okay, so this is just another sort of like vague curiosity about other things you could do with similar along similar lines. I feel like in practice, right, this is a very hard game to play, or it's very hard to implement any of these strategies, because unless you're like, you know, even with, you know, right, like how are you tabulating all of this in your brain? So I don't know, would it be interesting to think about a bounded memory variant of this, or has anyone thought about this?
Yeah, so that's a great question. So the second paper we have in preparation on this is called Practical Strategies for the Partial Feedback Model. So yes, we did
Cool.
do that. So for example, I didn't say what this strategy was that gave a
Right.
stronger lower bound, but it is
Uh-huh.
very simple. So what the strategy is what we'll do is we'll guess card type 1 for the first half of the game.
Uh-huh.
And then after that, if more than half the 1s showed up, we'll guess 2s for the rest of the game. Otherwise, we'll guess 1 for the rest of the game.
That's a
all you need
strategy.
to do.
That's a game
Yeah,
I
see,
can
I
play.
think I can
Yeah.
remember that. Yeah.
Yeah, so it's very simple, and it's the best bound that we can prove at least for in general. So yeah, so we do talk about some other simple strategies.
Okay. Yeah.
This very complicated thing that I blurred out is also relatively simple, though there's certainly a lot more details. But we do talk about it more in the paper, and yeah, it is I think it's an interesting question.
Okay. Cool. Yeah. Thanks.
Very clear.
Awesome. Any other questions? All right, let us thank the speaker once more, and then I'll stop recording.